and you can add S.M.Hadi.
If anyone's online that can just verify they see the slides. Okay, perfect, thank you. Okay, great. Thank you for the few minutes of setup, and thank you for the introduction. And so I'm a third-year PhD candidate at Stanford University, and I'll be presenting on simulation and control for soft-growing robots. This is an ongoing collaboration for my PhD thesis between the CHARM lab at Stanford University and the REX lab at Carnegie Mellon University. So I know the theme of today is discussing ways to address the challenges of soft robots and how we get a lot of great behaviors from the compliance, but then we have to sort out how to deal with them in modeling and control. And in a lot of overlapping themes, and so these will sort of be familiar at this point. And so the first is that we have complex dynamics for soft deformable robots. And then second, if we try to model contact interactions, that adds an extra layer of complexity. And then third, we often want to do these as fast as possible, often in real time. And so in our work, we're interested in developing a simulator framework that is suitable to motion planning. And so that sort of focus leads to the following goals for our work. And so the first is captures bending and growing behaviors, handles robot-object interactions, runs faster than real time, and then all three of these while being amenable to motion planning. And we are in particular focusing on a specific type of soft-growing robot. We call it a vine robot. And these flexible robots can grow to over 100 times their original length, and they've shown potential for use in medical applications as well as navigation and exploration. The core of a vine robot is an inflated beam, and material everts from the tip of the robot. As sort of a very basic demo, if we start with plastic tubing, on one end I've folded it back. And so if we consider this portion the tip of the robot, by hand I can reach in and pull material from the middle, and we have this length change. But for our vine robots, we sectorize the inside of the tube to achieve this growth. And so this video here is showing a unactuated steering, and so just from contact with your environment, you get turning and bends. And this scenario is the focus of our simulator framework. Before delving into the mechanics of the simulator, here are some example behaviors and scenarios that we can generate. These are showing both growth as well as bending behaviors and in multiple contact interactions. In the simulator framework, we abstract the vine robot as a series of rigid bodies, and they're connected via alternating pin joints and prismatic joints. We model bending behavior with torsion springs and dampers at the pin joints, and we model growth by elongation of the prismatic joints. In our framework, we treat the growth rate of each prismatic joint as a control input U, since we can use lower level feedback controllers to achieve a target growth rate. This use of prismatic joints as an abstraction is an abstraction of the actual mechanisms for growth. In reality, you've seen the video on the left where material is being added at the tip. However, instead of adding more rigid bodies to our model over time, we use these prismatic joints so that we can maintain the number of rigid body lengths that we're using in the model. And the purpose of this is to simplify the dynamics and simplify any integration with motion planning strategies. We handle interactions with the environment by enforcing contact constraints at specific points along the Vine robot, and we are showing them here in red. And this comes with, and so these can be summarized as 3 constraints. First, a contact point cannot be inside an object. Second, the normal force has to point away from the object. And third, a normal force can only be exerted when the distance between the object and the robot is zero. So this method of handling contact at discrete points is an approximation of the actual contact behavior, which can occur at any point along the entire length. However, this simplification still covers a variety of contact scenarios. Here are 2 examples. On the left, you see how multiple points, so the 3 red points, they approximate the line contact occurring between the Vine robot and the green rectangle. And then on the right, you can see how the sliding behavior is captured. So in our implementation, the contact points coincide with the pin joints, but this choice is arbitrary and a number of options are completely valid. So we could do something like add a higher density of contact points or shift their location to the centers of the link, and any of these would be reasonable. The main requirement is that the spacing between contact points remains relatively small. And this is relative to objects in the environment. So when problems arise, it would be an example like this, where first it is something feasible, and then in some intermediate time step, you have the Vine robot intersecting with an object, and then here again, we're okay. And the reason something like this would be generated by the simulator is if the red contact points are spaced too far apart. And so the rule of thumb is to keep it small relative to the size of objects. To compute the dynamics, we draw from methods for simulating rigid bodies, and specifically rigid bodies with contact. And in particular, we're using this maximal coordinate method. And so what that means is every rigid body has full degrees of freedom in our state vector. So we would be tracking x, y, and theta. When we look at the entire state vector for the robot, we're stacking the x, y, thetas for each of the rigid bodies, and then we also track their velocities. So those are the top and bottom halves of the state vector. Because we're using maximal coordinates and each body has full degrees of freedom, we then have to add in constraints in order to fully capture the behavior. So, for example, we would need a pin joint constraint that says 2 points on the 2 points, one on each body, that those 2 need to be coincident, and then a similar constraint for the prismatic joint. And then sort of looking at a top view, the benefits of the maximal coordinate method are in its simplicity. And so there are no recursive computations required to either propagate positions or forces along the length of the robot. And this benefit is achieved while matching the efficiency of traditional minimal coordinate techniques. And so using these concepts, we can write down the discrete equations of motion here. I won't go into the details of the expressions, but I'll go through the high-level components. So at the top, we have the discrete equations of motion. They're similar to Newton's equations of motion, but modified for maximal coordinates and for contact dynamics. We also include all system constraints. So the joint constraints would be the pin joints and prismatic joints. The growth constraints are the growth rates that we set via the control inputs. And then the contact constraints are the 3 requirements that we discussed earlier. So altogether, we have a system of implicit equations that relates the current state, the control input, and the next state. And we solve this by forming a convex optimization problem and leveraging existing efficient solvers. Before showing some examples, I wanted to talk a little bit about the design considerations that went into our implementation details. And ultimately, we're interested in integrating this with motion planning and control. And so amenability to classical motion planning and control strategies requires a dynamic simulator that is simple and fast. And sort of one other comment I wanted to add is that there's sort of previous examples where we use a model with lower fidelity in order to compute control commands at a faster rate. And so similar in our work, we're trying to finding a balance between model accuracy and computational complexity. So here's a little bit more detail. Our code is available on GitHub and the link there. It's written in Julia. And then on the left is sort of a sample program to generate the visualization on the right. So on the first step is to create the objects in the environment. Here we're creating a single rectangle. And then the second step is to create the Vine model, so inputting things like mass and inertia, and then also setting, for example, the time step length for the simulator. We also set the initial state for the animation. And then before we run the simulator, we have to define a couple other things. So one is this matrix V that will contain the state vector for each time step, and we just pre-allocate that. And then a matrix U, which has the growth rate for each prismatic joint for each time step. And so the last line here is calling the simulator. It'll automatically open the browser window on the right, and it's got some user interface to play the animation. Okay, so this next video is showing the qualitative agreement. This was just sort of hand-tuned parameters and sort of rough growth rate. So it's not a perfect fit, but shows the potential for the framework. The blue is the simulated Vine robot, and the yellow is the original video. And then to characterize the runtime performance, we ran an experiment for the video shown in the right. That particular one is 30 bodies and then a single circular object as the environment. But we varied the number of rigid bodies that we included and saw that we could get real-time, we could get a runtime for models with over 70 bodies to be in real time. So the time step was 10 milliseconds, and so we have the real-time threshold as the dotted line. So in order to bridge this into real gap, we propose a nonlinear least squares fitting method. And this is using video information from a real Vine robot. And we assume the presence of errors in both the video and the model. And so we are actually simultaneously solving for a trajectory of state, as well as the stiffness and damping parameters. So prior to solving the optimization problem, we extract useful information from the video. This includes evenly spaced points along the Vine robot, places where it's making contact with the environment, and the growth rates at each time step. And so our optimization function actually has 2 goals. The first is to minimize deviations from the video, and so our heuristic for this is the distance between evenly spaced points on the Vine robot in the video and that of the fit. The second second goal of the objective function is deviations from the model. And so if we have some current state vi, we can use our model F in order to generate the next state, but we allow for a little bit of deviation in the residual Ri. And so the purple is showing that we allow a little bit of deviation. And so we're trying to balance these two objectives. So the previous slide was for a single time step, but we can do this across an entire video segment and have this full optimization here. If you look in the upper right corner, that capital matrix R is just a weighting matrix so that we can sort of tune the weight between the first and second goals. So in addition to this objective, the bottom three lines are showing that we need to have a feasible trajectory. So those are the joint constraints. And then the growth and contact is to make sure that we match the information from the video. Here are some results from fitting parameters for two different scenarios. On the left, you have a beam which is oscillating from some initial displacement. And then on the right is a vine which is growing while in contact with a wall. In both cases, we're looking at a coordinate for the tip of the beam, so the y-coordinate on the left or the x-coordinate on the right. And so these results are showing that we can optimize parameters in scenarios for growth, bending, and contact. Quickly, the last topic I'll cover is about trajectory optimization. Since ultimately we're interested in applying our simulator for doing dynamic maneuvers,